Hi everyone, my name is Chanel D'Souza and I'll be talking to you about Lebesgue measure and non-measurable sets. You'll find it useful to have just a very basic understanding of countability, set operations, and equivalence relations. I'd like to start off with some history. Everything started to develop in 1902 with Lebesgue's theory of measure. This included integration, but we won't focus on that aspect. Now, what was the motivation for this theory of measure? Well, Lebesgue wanted to generalize the concept of volume, which is in 3 dimensions, to arbitrary sets. This is the concept of Lebesgue measure, which I'll often just refer to as measure. In 1 dimension, we know this is length, and in 2 dimensions is area. 3 years later, Giuseppe Vitali constructed a set that was not measurable. In 1924, Stefan Banach and Alfred Tarski introduced their famous paradox. And lastly, in 1970, Robert Solovay was able to show that there is a model of set theory that does not have these so-called non-measurable sets. Let's begin with introducing the Lebesgue measure, which requires defining what we call the outer or exterior measure. Shown here is the rigorous definition of the outer measure of a set, say A. Let's think in 3 dimensions to understand this definition. First, we begin by over-approximating the volume of the set A by closed cubes because we understand the volume of a closed cube well. This is done by covering the set with countably many closed cubes and summing up the volumes of the cubes. Looking at every possible way we can do this and taking the infimum, we get the outer measure. For our set A, the outer measure is denoted m star of A. The picture I have here is in 2 dimensions, so really it's area we're considering. If the set A is the red ellipse, this shows one possible covering of the set. You can imagine that as we look at every possible covering of the ellipse, we can make this approximation of its area better and better. In this way, the outer measure is always defined. Let's look at some simple sets and their outer measure. The first example is of a single point. Well, a point can be contained in a cube of arbitrarily small area, so its outer measure is just 0. Example 2 is of a cube, and as we would expect, its outer measure is the volume of the cube. The third example is of the rationals in 1 dimension. The rationals are countable, so we can cover each rational by an arbitrarily small interval. As a result, the outer measure here is again 0. In fact, you can use a similar argument to show any countable set has outer measure 0. The final example here is of the real numbers in 1 dimension, and I've put this example in to show that it is possible to have a set of infinite outer measure. So now that we have defined the outer measure, we can define what it means for a set to be measurable. Shown here is the rigorous definition. We say a set A is called measurable if for every positive epsilon, we can find an open set O containing A such that the outer measure of the set difference of O and A is at most epsilon. If this happens, the measure of A is its outer measure. Let's make this definition easier to understand. Measure is simply the outer measure restricted to sets that are in a sense close to open sets. This might seem like a strange definition, but we get some nice consequences out of it. The first consequence is that measure is countably additive. So for example, if we take a piece of paper and we cut it up into countably many pieces, the area of the paper is the same as if I sum up the area of the disjoint pieces of paper. The second consequence is translation invariance. So back to the piece of paper, if I move the paper over, either way, that is if I translate it, the area better stay the same, and this is exactly what happens. Finally, we have rotation invariance, meaning that if I rotate my paper, the area remains the same. These 3 consequences are really properties of volume that we want to retain when we generalize to arbitrary sets. So shown here are some examples of measurable sets. Examples 3 and 4 are called G delta and F sigma sets, respectively. In fact, examples 1 through 4 are part of a larger class of sets called Borel sets. Sets of outer measure 0 are measurable, so have measure 0. Lastly, complements of measurable sets are also measurable. So far, we've seen quite a few examples of measurable sets. Not only the ones I mentioned in the previous slide, but also the specific examples we saw when looking at outer measure. But does this mean that all sets are measurable, and if not, how would you go about constructing a non-measurable set? It is possible to construct a non-measurable set, and in 1905, Vitali came up with such a construction. We start by defining an equivalence relation on the closed interval 0, 1. 2 elements in the closed interval are equivalent if their difference is a rational number. So for instance, pi and square root 2, these are in different equivalence classes. So we're essentially just partitioning up the closed interval 0, 1 into uncountably many, countably sized equivalence classes. Next, we choose one element from each equivalence class and put them in a set called V. V is called a Vitali set and is not measurable. You can find the outline of the proof of why V is not measurable in my extended abstract. There's actually an even stronger and more general result shown by Vitali. The result is that we can find a non-measurable subset in any subset of the real numbers with positive outer measure. In defining the Vitali set, there is something that is key to the construction. When we chose one member of each equivalence class, we assumed something called the axiom of choice. The axiom of choice says that there exists a way to choose a representative of each set even if you cannot explicitly define it. The existence of non-measurable sets is contingent on the axiom of choice. And an interesting consequence here is that the cardinality of the non-measurable sets is the same as the cardinality of measurable sets, both being equivalent to the cardinality of the power set of R. So there seems to be a whole lot of non-measurable sets. This leads us to two options. Should we accept the axiom of choice or reject it? Well, let's say we accept the axiom of choice. That is, we accept non-measurable sets. Are there any strange things that happen? Well, one of the most famous examples is that of the Banach-Tarski paradox. This paradox says that a three-dimensional unit ball can be decomposed into a finite number of disjoint sets that can be reassembled using only translations and rotations into two-unit balls. So it seems like we're creating something out of nothing. Although we're kind of cheating. Some of the sets in the decomposition are non-measurable, so we're not really able to say anything about their measure. Another formulation of this paradox is the P and the sun paradox. This is very similar in that we can decompose the P into pieces and rearrange them to be as big as the sun. The point of this is that something small can be cut up and made into something huge, which physically doesn't make any sense to us. These are some of the strange consequences that arise when we accept non-measurable sets. And if you find these too weird, let's reject the axiom of choice and see what happens. In 1970, Robert Solovay was able to show that there is a certain model of set theory where we have no non-measurable sets. This is a model of Zermelo-Fraenkel set theory without the axiom of choice. By this, I mean uncountable choice. There are 9 axioms of Zermelo-Fraenkel set theory, but here we are rejecting the 9th axiom, the axiom of choice. If every set is measurable, one consequence is that every function can be integrated. What I mean is that there exists a reasonable way to define area under a curve. Here I'm speaking in R2. This involves using measure and is called a Lebesgue integral. The area might be infinite, but we never have a case where the function cannot be integrated because everything has an area. However, if we allow for non-measurable sets, certain functions cannot be integrated. So what I'm getting at here is that you can either accept or reject choice. Most mathematicians opt to accept, but we can't seem to win because with this choice, there is no explicit representation of the non-measurable set. So now let's backtrack to outer measure. I want to leave you with some questions to consider. As mentioned before, every set has an outer measure. So what is the outer measure of the Vitali set we constructed? Well, it can't be 0 or it would be measurable, and it can't be 1 because then its complement would be measurable. It must be between 0 and 1 because we were working with the closed interval 0, 1, but there is not enough information to determine what it is. This leads to the question of if there is another way to construct a non-measurable set of any given outer measure. There's actually a way to do this if you're willing to say something about the choice function, but I'll leave that to you to ponder. Here are some references that will give you further detail into the concepts I touched upon. Thanks for listening.